All right, good morning, guys. Let's get started. Sorry for the smell. We're gonna have nice flowers and trees out there, I guess. So that's the benefit of our campus smelling like crap. Happy Thursday. Yeah, we are doing permeability. This is a cool topic because it kind of overlaps in a lot of your other classes. If you take hydraulics or any of those courses or any of the environmental courses, this is one of those like little overlaps on the Venn diagram between engineering and environmental engineering. But it's super, super important for Florida. So if you're thinking about sticking around working in Florida in any type of engineering, you'll definitely see these properties and they're important and that stuff. So we are doing these two chapters. I also wanted to go quickly over the schedule just so we can see where we are. Thankfully, we're almost to this week, which means we're almost to this week. And then after that, I just wanted to remind you guys that next week, March 22nd and March 24th, there's not going to be in-class lectures, so you don't have to show up at 8 a.m. I'm going to be posting 2 videos that kind of go over some of the online tools that you will use for your final lab. So there's also no lab sections that week too, obviously. And then the week after that, March 29th, we'll have our exam review, and then March 31st, we'll have our exam. So really after next week, we are going to not have like some in-class lectures for quite some time. So stay up to date with everything. Yeah, we are ahead a little bit. Yeah, so we ended up completing compaction. So we're starting soil permeability today. For you guys who are looking to find the moisture contents for your lab, the Tuesday and Wednesday group, today we should end a little early, so I'll unlock the lab and you can go do that, or you can come back after the lab section today around like 10. I'll just leave the lab door open and you can go and take your moisture contents for that. And spoiler alert for the people who are doing a lab today, we're doing moisture contents. Let's see, is there any other announcements? If you're planning on doing ASCE, if you're going to the conference, there is a mandatory meeting today. You got to sign one of the forms. So hopefully you've seen a message from Brody already. If you're not planning on going, then don't worry about it. Nice shirt, by the way, too. Free swag there from the career fair. The logos of these like engineering companies now are so cool too. They're getting hip and stuff. Hope everybody had a good time at the career fair if you were able to make it. If not, still, I encourage you guys to go next time because it's good just to meet people, even if you have a job. And you're going to be working with these people, whether you work for them or with them in the future. So you might as well get to know them and stuff like that. Any questions on where we're at in the class so far? Schedule makes sense. Everyone's going to do something fun for spring break and not study the whole time. I think that's one of the requirements of this class. Get ready for conference and stuff. Okay, well, let's get started then. Soil permeability. Has everyone heard of the term permeability before? Do you guys cover this in your other classes a little bit? Maybe. Okay. This is a very obvious soil property. We know that if you go to the beach and you pour a water bottle out or whatever you're drinking at the beach, then that's not going to sit at the surface of the sand. It's going to flow underground and through the pore space. So that is an important property also for engineers to understand how the water can move through that pore space of the soil. So the whole reason why it is able to do that is because we zoom in again, looking at the 3 phases of our soil. And we know that in its natural state, there is solid water and air. So it looks something like this. My little drawing here, since I have a Microsoft pen, I can draw stuff now. And normally what we would have in just a snapshot condition is what we would call hydrostatic conditions. So static is just a fancy way that us engineers use to say stuff isn't moving. So hydrostatic is there is no movement of water. All the things are chilling, they're fine. The energy is all equal. And this is normally how we would like calculate like a best case scenario for our subsurface conditions. So that means most of the time this happens when we are in an unsaturated case. So unsaturated soil, again, saturation is the volume of water divided by the volume of voids. Then we multiply that by 100. So anytime S is less than 100%, for the purpose of this class, we are assuming that it's always going to be hydrostatic. So the permeability of a soil, or so for water to flow through the pore space, we need saturated conditions. So like for this case, like water is not going to be able to flow through this because there is these empty air bubbles blocking it. But of course, the opposite side of that, if we have hydrostatic conditions, who wants to guess what the other term is going to be? You take statics. Yeah, exactly. You take statics, everything is equal to 0. Dynamics, everything is equal to something, you know, F equals ma, which doesn't equal 0. So this is the movement of water, which means we have flow through the water. So now all of these interconnected pores are all filled with a medium of water. So there's train tracks connecting everything and it can flow through the pore space. And we're all happy and we're able to actually mathematically define. So realistically, permeability and flow through water can actually occur in unsaturated soil. But we are not able to use our fancy equations and mathematical relationships for unsaturated soil flow. But there's a whole nother topic. Usually that's like a grad class. I only took one class in unsaturated soil mechanics, but like the permeability in unsaturated cases still occur. For this class, it's always going to be saturated. So this is, of course, here, the saturated soil. This is when it's equal to 0. And in this case, if we have any change in energy, like thinking back to Bernoulli's equation from your fluid dynamics class or your fluid mechanics, we have any change in that Bernoulli's equation, then we're going to have a movement of water through the pore space. And it can occur because all of these little connected tunnels in the pores are filled with water. So this is really important for just the natural side of things of geotechnical engineering, like understanding the groundwater system. Like have we all seen like something like this before, this little cartoon where you have, you know, precipitation going to a stream, and then evaporation, and then the magic of like clouds bringing it back over here. We have the water cycle. So for a geo-environmental aspect, you know, understanding how the groundwater is going to flow, like the time it takes for it to flow from one side to the other is important. And then this is like the idealized, like simplistic case. Of course, in Florida, we have it a little bit more complicated, but a little bit more interesting because we have this karst system where we have levels of permeability. We have water flowing through soil, as well as water flowing through the cavities of the limestone and stuff too. So you can see for engineering purposes in Florida, it gets much more complicated. And so we need to be able to understand the micro and macro permeability of our soil. So macro permeability would be the flow through these conduit systems that you see, like the little cave divers going through and everything. Micro permeability, the ones that we care about as engineers and talk about here, that's the flow through the pore space of the soil. So not only is it important from like a geo-environmental aspect, you know, we want to dig a well and we want to make sure we have enough water coming up for our residents, or we want to make sure that if we are putting a septic tank in a household, it's not flowing into an area where we're drinking water. It's also important from like a geotechnical, like a design of foundations and analysis point of view too. So retaining walls, I've shown some pictures of these before. If you take design and analysis foundations with me, we'll get more into the actual like design of these retaining walls. But you can probably imagine what these retaining walls are used for, right? They're meant to retain earth and allow us to change the ground surface elevation so we can put our parking structures or our basements or any type of structure below grade, below the ground. Now in Florida, of course, the groundwater table is going to be pretty high. So not only do these retaining walls need to hold back earth, soil, but they also need to hold back water. Now this one is kind of hard to see, but if we design the flow of water, and we're designing these retaining systems to limit the flow of water, then we need to make sure that we design it consistently. So in this, you zoom in right in there, you see there's a small little seepage issue where the permeability of the soil in this area was not what we expected. And now there is flow of water, the groundwater coming from one side to the other. So you could probably imagine, like with seepage, as soon as we have any initiation, then the erosion is going to start occurring more rapidly and rapidly. It's a progressive process. So even though we have just one little slight miscalculation or one construction issue in this point, it can quickly escalate into a massive failure. And now we have a fun lake instead of a actual retention or an actual excavation in this case. So understanding the permeability of our soil, especially if we are manufacturing soil. So if we're trying to limit the permeability through an embankment or through a excavation like this, it's very important because one little mistake can escalate into millions and millions of dollars. I think this is in either Egypt or Dubai, so it's not in Florida, because that'd be a big issue if so. But we still have things like this in Florida. Do you have a question?
Yeah, is there any way to stop the seepage?
I mean, they could try to pump it. You could do shotcrete, so they could go in with like spray cement. But most of the time, when the energy finds a path to, of least resistance, it's going to start going pretty quick. So yeah, there's issues. There's a lot of other, like they could do 2 layers of impermeable, so like they have a redundancy level if it's like this. But once it starts like this, then there's big issues. You can see they brought pumps in trying to stop it, but it wasn't enough because it's such a progressive thing. That little pump's not going to really do much with everything. So although we don't have excavations like this in Florida, we have these, and these are everywhere, especially if you live in South Florida, like near Lake Okeechobee or where the St. Johns River is like, originating from, like down in like south of Brevard County. We have these earth dams and we have like dikes, which are used to manage the stormwater and then channel the groundwater into like the correct areas so we don't have flooding or anything like that. And all of these, although they just look like, these mounds of earth, if you were to take a giant slice down the center, what you would see is there are 2 layers of most of them. And there's actually these clay cores in the center that are meant to limit the groundwater flow. So what we've already talked about in the lab sections is like sand compared to clay. Clay has much, much lower permeability. And you can probably picture that if you had a mound of sand versus a block of clay and you poured water on both, the sand would look like absorb the water, and then the water would just pond on top of it, right? So we use that low permeability to our advantage in cases like this, where we're trying to block water on one side and we don't want it coming to the other side. I think actually one of the longest earth dams or dikes here, this is Lake Okeechobee. I think now oh God, I'm not even gonna be able to spell it. Okeechobee. The whole perimeter of Lake Okeechobee now is surrounded by one of these clay core dams. So with that, they're being able to greatly reduce the risk of flooding, because now Lake Okeechobee can rise and fall and have more like freedom to do so without spilling over. But we also have other types of earth dams that are called homogeneous earth dams. And homogeneous earth dams look like this, and this is where the material, if we were to take a cross section, the soil that it's made of is all consistent, so it's homogeneous. We don't have a difference between like a sand layer and a clay layer. So these are meant to allow permeability, so water to flow through them, but it's meant to control them. So what we have is a filter, usually at the end, or some like like low or high permeable gravel or boulders or something. So all the water that's flowing through it will get channeled to this one area, and then we can either divert it away or pump it off to a different location so we can safely mitigate it. So I don't know if you guys cover this in any other classes. We'll touch on it a little bit later in the semester when we start looking at the flow nets. But all of the property of soil, so the way this permeability of this soil is huge when we're looking at actually designing these. Same with the clay cores, right? The permeability of this is an important soil property. So that's what we're introducing today. So we know soils are permeable, that term permeable, due to the existence of these interconnected voids through which water can flow from points of high energy, from points to low energy. If you're unfamiliar with thinking of water flow in terms of energy, then it can get kind of confusing, but we know, like, obviously, like, water always wants to equal out. Like, if you have water in a cup and you pour it over, gravity is going to want to pull it down to its lowest potential energy state. And it's the same when we have like interconnected, voids, like, toilets work because water wants to flow down into the sewer system, that kind of stuff. So it's same whenever the water is in the pore space of soil. And this greatly affects our design equations for seepage and leakage through dams or levees. So like what we showed like on the previous slide. And then also, this is huge when we start talking about erosion. So like the flow of water through the pore space of soil can actually cause, if it's great enough through the pore space of soil, can actually cause those individual soil grains to move up against each other in isolated areas underground. And then if it gets great enough, seepage underneath, great enough seepage forces, then the soil particles can actually dislodge, and then we can have internal erosion. And then that's actually what occurs with sinkholes underground. That's like what forms sinkholes propagating up to the ground surface. A big area too that we talk about is consolidation. We're briefly going to cover this at the end of class, but this is settling of clays long term. So the best way to think of this is like if you have like some sponge, like some of these super nice, expensive, like car wash sponges that have really small void spaces, like, and they're filled with water and you squeeze them, it takes a little pressure, it takes a little time to squeeze to remove all the water out. So the same thing happens with clay, except over years and years. Like if we put a building on top of clays, it's slowly going to squeeze all the water and it's going to settle. And that term is called consolidation. And that's related to the permeability of the clay. Dewatering, so pumping of groundwater sites. This is huge in Florida. Whenever we do the lab here showing up, I'll show some pictures. Even if you don't know what you're looking at, most construction sites will have these dewatering pipes. It's like one single white pipe and then all these little spider pipes coming off of it. What they're doing is trying to dewater the site so they can go and the excavator won't get stuck as they are building the new roadway or something. You've definitely probably seen pictures of it before or seen it along the highway. But in order to know how much we need to run the pump for how long, we need to know what the rate of the water flowing through the soil is. So that's the permeability. And then also for the stability of other things, this like gets into like what we call like drained conditions. And that controls like the strength of our soil too. So we won't get into this too much in this class, but if you're planning on taking the tech elective with me, store that word in the back of your mind, that drained conditions. We'll talk a lot about that and how that affects the soil strength over time. So this soil property that we use to define all of these things is called the permeability coefficient. Permeability coefficient, 9 out of 10 places, it's going to be represented by a K, like so just a little sideways K like that, or the italicized Ks. It's always going to be in the units of like a length per time. So centimeters per second is the most like typical way of showing it, but it could also be like feet per day too. That's also another way of showing it. The units usually reflect who's doing the calculation. So if you're a stormwater engineer and you're working with massive amounts of water flowing through a pond. And most of the time you're going to be looking at feet per day, because we're talking about like, like big scale macro permeability. For us civil engineers, when we're looking at clays or silts, and we're talking about like a slow movement of water through an earth dam, then we usually show it in centimeters per second, because it's a little bit easier to conceptually like understand what those numbers mean. So soil permeability, another phrase or another term that you will hear is the hydraulic conductivity. So permeability coefficient could technically be any type of fluid. Gas traveling through pore space of soil, that could have a permeability coefficient. Even petroleum or oil deposits traveling through rock, like they will have a permeability coefficient. So the permeability coefficient is dependent on the material itself, like the viscosity, right? Like an oil deposit is obviously going to flow much slower because it's a thicker viscous material compared to a water like aquifer or something like that. So if we're talking specifically about water, most of the time we just refer to it as hydraulic conductivity. So in your other classes, I'm sure Dr. Khan's class or any of the water-based coastal classes, you may hear this term as hydraulic conductivity. It's the same as permeability coefficient, just specific to water. So when you're looking through textbooks and stuff, just keep in mind that. So the flow of water in soils, like everything else for geotech, we take this big like macro, like physical issue of water flowing through pore space, and then we slap a bunch of assumptions on it, and then we can create a nice, neat mathematical relationship and function that allows us to define or quantitatively define this intrinsic soil property. So the first thing that we are assuming when we're talking about seepage analysis in soil is that water is incompressible. So you'll see this trend a lot in geotechnical engineering. This is like a major assumption. What that means is that the delta volume, so the change of volume in water, is equal to 0. So no matter how much you load, how much pressure you put water under, it's never going to change in volume. Now we know this isn't true because like realistically, like water is compressible, because if you put in water in a pressure like vessel, it's going to turn into gas and the volume is going to change. But under the conditions that we care about in groundwater, we're assuming that this delta V is always equal to 0, and water is always incompressible. And this is also, if you remember the Poisson's ratio, that means the water has a Poisson's ratio of 0.5. So any loading in the vertical direction is going to have an equal and opposite loading, or sorry, any deformation in the vertical direction is going to have an equal and opposite deformation in the lateral direction. So we're squeezing this way, it's going out the other way. The other thing that we are assuming with flow of water in soils that we don't get to assume in your hydraulics class is that flow is always laminar. Has everyone heard this term before? Laminar. So this is like the nice, peaceful version of flow. So if you go to like during the hurricanes or something and you see some of these or like rivers or canals or something, and they're just choked with water and there's all these white water and there's turbulence all over the place, that is not what we're talking about here. For laminar flow, the flow line is always parallel. So if we were to have an open channel or something like this, that means all the little flow vectors would be nice and parallel. There'd be no interchanging and no like change, like overlap with each other. And so this is generally associated with a slower velocity flow. And in the groundwater systems like flow through soil, it's so low that we're assuming it's always going to be laminar conditions. The other thing is we are assuming a conservation of mass. So that means that the flow of water into a system is equal to the flow of water out of the system. So this is really big because this is important. This is where we assume that this saturation is equal to 100%, right? Because if we didn't have saturation at 100%, that would mean that there would be air voids in our soil, and any water coming in could get trapped in those air voids and not subsequently leave our soil. So when we have a saturation of 100%, that means all the water flowing in is going to flow out. It's like having a cup of water that is completely full and then pouring more water on top of it. That water has nowhere to go. It has to flow out of our cup. So this essentially means that there is no absorption. Absorption. So this is also something different than our gravel and our aggregate from CE materials. Like for that, we could see that there was some absorption of the water into the actual grain rocks itself. But when it comes to soil, we're assuming that the grains are so small that there is no water absorption occurring on the individual granule level. So this is a really important one, conservation of mass. The other one is the conservation of energy. So that's Bernoulli's equation. This is just telling us, like, if you remember the different head losses and all that fun stuff, like all changes of energy can be accounted for through Bernoulli's equation. So we either have the elevation head, the pressure head, and the velocity head. And then we'll get into more of those details here in a second. But those are the four key assumptions for us to be able to derive these equations that we use to understand the permeability of the soil. So flow of water, there's a lot on here. Let's just start here for the open pipe right here on the left. So we already, has everyone taken like fluid mechanics or something? You know that like the flow of water through a pipe is equal to the cross-sectional area of that pipe times the velocity, right? Q equals AV. So that's essentially what we're seeing here. So if we picture soil like as a pipe filled with some type of material, like the pore space of the soil is just a crudely drawn curvy tube, then we can have the same relationship, but now we have some type of medium in here. That's the granule spaces, right? Or that's the actual soil grains in there. So we still have Q equals AV, but now our flow area is different because it's blocked because we have soil grains in there. So if you remember when we were doing the original phase diagrams and everything, we talked about void ratio and we talked about porosity and how they're very related. You know, there's that one equation that turns in between the two. And I said, just forget about porosity for now because we use that heavily in permeability. This is it now. So you can see here, our flow area is directly proportional to the porosity. So our area of open void, in this case, if we're idealizing a soil, tube that has a soil in it, then that area is equal to the porosity times the total area of that. So in most geotechnical engineering problems, it's easy to measure the discharge velocity and then the total area of like a tube that we have filled with soil or something. So in that case, since our porosity is the volume of voids divided by the total volume, and if that we're looking at just like a cross section instead, then the total voids divided by the total volume is also equal to the total area, or sorry, the area voids divided by the total area. And that means what we have is the actual velocity of water going through our soil is equal to the discharge velocity divided by the porosity. So this N, again, is the porosity. So let me reiterate what's going on. So discharge velocity, if we have a tank of soil and we're pouring water at the top of this soil, like a big, tank of soil or whatever, we're pouring water at the top and we have a little spigot on the side, we see the water leaving the soil tank. So this is the discharge velocity. We can measure that. Its velocity is like feet per second or something. So we could take a little tube and we could measure like how much feet of water is leaving the soil per whatever seconds or minutes that we're measuring. If we take the phase diagram and we go through and we calculate the porosity of our soil in the tank, then we can determine the velocity of the water particles within the soil by dividing it by the porosity. So the discharge velocity, what we're measuring, divided by the porosity is what's actually happening inside the soil. And what's happening inside the soil is important because what's happening inside the soil affects our stress and affects the potential for erosion, right? So the discharge velocity is easy to measure, but the discharge velocity is easy to measure, but the seepage velocity is the important property that we need as geotechnical engineers. So this is all based off of the conservation of energy. So from fluid mechanics, we have a special term that is corresponding to the energy level, or that is measured in height of water, and that is called our head, right? If you remember that term. This is literally like just showing it in feet. So usually we show this is because we can correspond this to elevations. So if we know we have a pressure head of 50 feet and the ground surface elevation is like 45 feet, then we can easily determine like how much water will rise, or what, you know, we do it in terms of elevation. So what we will look at is the total head. This isn't working. In our Bernoulli equation, and this is by HT, usually subscript T, or sometimes it's just shown as like a capital H, depending on who's looking at it. And this represents the total energy available for the water to drive through the soil voids. So we need to think and like try to think of it as energy. So this is the driving force that is causing soil to flow, because if everything is equal, if there's no differentiation in energy, then we have hydrostatic conditions. So there's no movement. So as soon as one person has more, or one side has more energy than the other, then things are going to want to try to balance out. So what we see is the total head is equal to three things, and this is from our Bernoulli equation. It's equal to the pressure head, so HP, and this is the energy stored as pressure in the water, so kind of obvious. It's equal to the velocity head, which is our HV. And this is the kinetic energy. So if we know the kinetic energy is 1/2 mass times the velocity squared, and this is how we get this equation. Actually, this should be 2 here. Yeah. As we look at it at such a small level where the mass is, you know, negligible, so we're looking at only, or the mass is consistent, where water has consistent mass, we're assuming, so that we're able to take out that mass term. And then we also have the elevation head, so HZ. So this is a potential energy. So this literally is just like where the water is, you know, according to some datum, like the ground, like the mean sea level, or it could be any datum, but it's like that baseline measurement for all the comparisons. So what we do is we plug this in, and this then would be like how we could calculate using Bernoulli's equation for any type of groundwater or any type of condition. So like open channel flow, right? Any type of conditions here, pipe flow, anything like that. So this is Bernoulli's equation. But when we're looking at water, we have a specific case. So we can actually simplify this a little bit further. So when we're looking at a flow of water through soil. So the flow of water through soil, what we know is like if we have static conditions, then our velocity is going to equal 0. So our total head is just equal to the pressure head plus the elevation head. So at this lake surface, let's say we have like an example like this, and we want to find the energy levels through this entire cross section. At the lake surface, if our datum is here at 0, then our elevation head is 50 feet, right? Because we're up here at point A, 50 feet. And our pressure head, how much water is above it? There is none. So this is equal to 0. So what we would see is our total head at A is equal to 50 plus 0, which is equal to 50 feet. So let's look at the mid-depth layer. So our pressure head is equal to the height of water above it. So how much pressure of water is above that point? And that is equal to, there's 25 feet above us. And we multiply it by the density of water, which is 62.4 pounds per cubic foot. And that is equal to 1560 pounds per square foot. So our elevation head at this location is 25 feet off of the baseline, that Z equals 0. So that means our actual pressure, our total pressure, so this is total head, is 1560 PSF, and then we divide it by the unit weight of water again. And then plus the velocity head of 0, since we still have no flow. And then plus 25 feet. And you'll see that our total head again is 50 feet. And hopefully this is making sense because there is no flow in this case. So since there's no change, there's no flow of water, then no matter how deep we go, we should see the same amount of total energy, because you only have flow if the energy changes, because we're trying to have it balance out in equilibrium. So you can probably imagine at point C, it's going to be all the same stuff. So let's just calculate our pressure head still. Our height of water is 50 feet at point C, since we have 50 feet above us. And there's 50 feet of water here, times the unit weight of water, 62.4 pounds per cubic foot. And so that's equal to 3,120 pounds per square foot. So that's our pressure. So then our total head, this time we have same thing for our pressure head, which is 3,120 divided by 62.4, plus our elevation head, or sorry, plus our velocity head, which is 0, plus our elevation head, which is 0, Z is equal to 0. You'll see 50 feet. So this is really just to show you mathematically how each one of these three combinations, or how each one of these three like contributing factors actually plays a role. You know, like in this simple lake case where we know there's no flow, and we know that, okay, the water, the pressure head is staying the same, we can still see Bernoulli's equation still applies for all of this stuff. So let's say, so that hopefully this makes sense, because what this pressure head, you'll see in this class, this total head is often represented by like these like little tubes sticking out. So what this is actually telling us is how much water will rise. That total head is how much water will rise in like a theoretical tube if we were to stick it in that spot. So in this case, since we have no flow and everything is equal, then the elevation in each one of these tubes, regardless of the depth at which the tube is placed, is all going to be equal. So our total head at point A is equal to all of them. And so since the energy is equal through the entire column, that means there is no flow and it is hydrostatic. So what would happen then if we came in with some pump or something and we decided to pump at this spot and then subsequently lower the pressure head to a lower elevation? We would see water want to move this way, right? And since this is just open water, then it would probably move unimpeded. And that's like when you have like these little whirlpools at the surface and everything. But if this whole thing was filled with soil, the water is going to not move as quick, right? So we're going to have some resistance to water flow, and that's the important thing of permeability. So water flow occurs in soil, and what we assume though with this, if we remember back to the Bernoulli's equation, what we assume is since it's laminar flow, that this velocity head is equal to 0. So what we say is that the velocity is so small. So when we square it, it is so much less than the, it's so much less than our 2g here. Let's pretend that's a fraction, that it goes to 0. So our Bernoulli equation for flow of water in soil is only 2 terms. So now we have our pressure head plus our elevation. So that's nice. So it makes stuff easier. And again, this is all because of the assumption that laminar flow is occurring and that what we call Darcy conditions are occurring. Yeah.
What's the U?
The U is the pore water, the pressure. So the U here from Bernoulli's equation, right here, our HP is equal to the pore water pressure, which is basically like the height of water above you times the density of that material. So if you were in a swimming pool and you swim down 10 feet, you feel your ears, like the pressure on your ears increase. And that's because you have a height of a substance above you. And so that height of the water above you, you could calculate the pressure on your ears by that equation. But let's say for whatever reason you were swimming in Jello or something instead. That'd probably be dangerous. Some other liquid that's not water, you could calculate the pressure on your ears by multiplying it by that unit weight of that material. So that could change. But in water cases, that pressure head is always going to be the unit weight of water. Okay, so since we know we are assuming the conservation of energy, so the water head is staying consistent through the entire thing, what we would see is this at this location, if we were to stick a tube at one part of the soil, at the upstream end of the soil, and then stick another tube at the downstream end of the soil, the seepage velocity, we will see our total heads are going to create a distinct slope. So it's going to be constant. This slope isn't going to change. And what we call that slope, sorry, I wrote this here in the wrong spot. What we call that slope is called the hydraulic grade line. So we see that in open channel flow, like from your fluid mechanics classes, but we also see the same thing in soil as well. So that would mean that if we were to stick tubes anywhere along here, that we could estimate the height at which the water is rising on because it follows that distinct hydraulic grade line slope. So this slope in laminar flow conditions where there's turbulence and assuming conservation of energy, that slope of the hydraulic grade line is something that we call the hydraulic gradient. So that hydraulic gradient is I, which is represented by I, and it's just the change of head divided by the length of the flow. Now, the important thing is this length is the length that is parallel to the flow. It's always going to be parallel to the flow. So in this case, in this, like, the idealized pipe filled with soil, it's tilted at an angle. The flow lines are going this direction. So our length needs to go that direction as well. So if you have flow going vertically, like in, if you pour, like if you have that tube or that whatever, that big like container of soil again, and we pour water at the top and the water trickles down, then the length is going to really be a height. So always think of it that way. Like it's not necessarily lengthwise, like horizontally, it's just the length of the flow lines. In this case, like this could technically be the length too. Like if we had some bucket of water and it's flowing out there. So the flow of water in soil, has anyone heard Darcy's law before? It's really popular in like groundwater classes and stuff too. But if you haven't taken that, or if you're not familiar with it, then it's okay. Darcy's law, way back in 1856. What they determined was that the discharge velocity is inversely proportional to, I don't know how to draw that cool little sign. Proportional, it's like something like that, to the hydraulic gradient. So for specific to soil, this is all dependent on soil gradation, the angularity, and compaction. So in Darcy's law, what he's saying here, like mathematically, is the velocity is equal to, sorry, I guess this shouldn't be, this is not inversely proportional. This is directly proportional. I don't know what that means. I'm just going to write directly proportional. So it's equal to the hydraulic gradient, but the soil gradation, the angularity, the compaction, all of this stuff needs to be encompassed into a variable. And that variable, bring it back to the beginning, is our K. So all of these soil properties that are changing this relationship, we know it's always going to be a directly proportional, like velocity and hydraulic gradient, but there's still some contributing factors, and we encompass all of that into this K value, and that K value is our permeability coefficient of soil. And of course, this is the hydraulic conductivity too, and it's always shown in, yeah, something like this, feet per day, something like that. So the velocity of the water, the discharge velocity, so that's important. This isn't the seepage velocity, this is the discharge velocity. And that is equal to Ki. Now, velocity, sometimes we actually want to care about flow, right? Like we want to know what is the actual cubic volume amount of water traveling out of a soil condition or into the aquifer or something. So to do that, knowing that the flow Q is equal to our velocity times the area, Q equals AV, then that means it is equal to Ki times A. So that is Darcy's law, assuming laminar conditions, assuming all those things, water is incompressible, the flow is negligible because it's laminar. But if we have that, then we can mathematically define and estimate the soil or the amount of water flowing out of a soil condition, because it is equal to the permeability coefficient times the hydraulic gradient, so the energy applied to our soil, and then times A, the cross-sectional area. So these, we have to remember though, this Q is discharge, not the seepage. So not internally, that's what's actually leaving our soil. So we need to divide it by the porosity, the velocity divided by the porosity to determine the seepage one. So the permeability coefficients, these are some of the values. Just generally what we see is the smaller the size of the sample. So clay particles are going to have the smallest permeability coefficient, and then clean gravel and like large aggregate, that's all going to have some of the larger permeability coefficients. For geotechnical engineering, most times we're going to show them just in generic numbers, like in terms of like 100 centimeters per second, or 10 times 10 to the negative 9 centimeters per second, etc., something like that. Only for specific projects will you need to actually like specifically quantify and be exact when it comes to the permeability coefficient. But in general, you just show it as these. And they depend on a lot of things. So it depends on the fluid viscosity. So the permeability coefficient of salt water is going to be different than fresh water because the water is changing, It's going to depend on the grain size distribution. This is why that sieve analysis and also the hydrometer lab is really important. It's dependent on the void ratio, which is also meaning it's dependent on the compaction. And it's also dependent on the flow of fluid and the saturation. So that's why for this class, we always assume laminar. And we always assume S equals 100%. Because what we actually see realistically, this real world here, real word, come on. The real world, what we actually see is that the relationship between velocity and hydraulic gradient, when we reach out of the laminar conditions, it doesn't follow a straight line anymore. So this is non-laminar. And all of this is laminar. So if it follows a straight line, if that velocity and hydraulic gradient are just directly related by the straight line, then the slope of this line is our K value. But if we go beyond the laminar conditions into transition or turbulent, then it doesn't follow that. So we can't use this K value to relate these two terms. So the permeability coefficient you cannot calculate it for transition zone or turbulent flow. I wanted to show just a few examples of the importance of this. Last class, we finished by talking about like the compaction effort and the optimum moisture content and how we could have like a wet of the optimum or dry of the optimum. And I showed that last slide on the last class, how it's like it's up to the contractor, like there's pros and cons for each side, even though we can achieve that density that we need. This is a good plot that shows the direct relationship of permeability and the water content, and if you're compacting wet or dry of the optimum. So down here, this is our compaction curve. That's what we talked about last week. So from this, you can see where our optimum moisture content is right here, right? So this would be our dry max. And then this value here would be our optimum moisture content. And then I also talked about last week or last class how it's hard to get exactly in the field, it's hard to get it exactly at the optimum moisture content. So we usually have an acceptable range, so like 95% or something. So if we have that like 95% criteria right here, that means there is acceptable ranges of moisture. And you could either go past the optimum moisture content, so too much water, or you could go less and still achieve that. But if we read that up and read the corresponding permeability coefficients, the optimum moisture content of the permeability is right here. And although the densities are the same, the permeability coefficient dry of the optimum is much, much lower than it is wet of the optimum. So you can see this would be our dry of the optimum, and then this would be our wet of the optimum. So same density, contractor point of view or engineer point of view, they're like, okay, like we met our goal on the same density, we're good to go. But you can see the difference in the permeability still here. That's times 10 to the -7 versus times 10 to the -5. So like move the decimal places over two places, even though all the other properties are the same. So this is a good example of how that compaction effort, is you need to control it and how it can affect the actual permeability of a sample. Let's see, is this a short example? Okay, so let's look at a really short example here. you'll see a lot of like textbooks and even on your FE like show something like this, where you have these two pipes coming up and then you have a tube of soil right in the center. And you're like, okay, like what is this actually representing realistically? These are idealized like ways of showing stuff like this, like an earth dam or something, you know, like if you think about it, we have a lake on one side that has a specific elevation. On the other side, it usually goes into like a creek or something. So we have this change of energy between like the upstream and downstream side. And then we have soil in between it blocking. So that's literally what this is showing. So this soil here could be like the clay core or something like that, or the earth dam. Sorry, let me change this. This is just an example. So with this, we know that the head upstream is not equal to the head downstream. So that means we are going to have some type of flow. So we have hydrodynamic conditions, flow of water. That flow is going to want to enter the soil here and then leave the soil there. So let's just say, like, for example, this L here, this length of our clay core is 100 feet. How can we find the discharge velocity of this? So we know that the discharge velocity through Bernoulli's, assuming all of those assumptions that we just had, is equal to the hydraulic gradient times the permeability coefficient. So what you would need is first to find the hydraulic gradient up here. A hydraulic gradient, the change in head is 30 feet. We're just told that you could measure that, you know, at the project site, you see the lake is at this elevation, the downstream is at this elevation, subtract the two, our delta H is that. And then the length at which the water is traveling. So this direction is 100 feet. So our hydraulic gradient is 0.3. Note that the hydraulic gradient is always unitless. So if our length was provided in meters and our change in height was provided in centimeters or so on and so forth, then you always need to convert them into the same units so they cancel out. And then let's just say like we've done lab permeability tests like we're going to do in a few weeks. And we found that the permeability coefficient of this soil is 0.002 centimeters per second. So our discharge velocity, what is the actual velocity leaving our soil? So right here, again, discharge leaving it. We just multiply those two. And we see that our discharge velocity is 6 times 10 to the 4 centimeters per second. So that's how much, that's the velocity of the water leaving our soil. But the seepage velocity is also equally as important. So if we like think about biological processes or something, like a lot of times like we want water to slowly move through the pore space of soil so it has enough time to be treated with biological processes, like for wastewater treatment or like stormwater treatment. We want the water to take time so microbes and everything can slowly, you know, eat whatever happens chemistry or biologically. I don't know all that stuff, but we sometimes want it to slow down through the water column so that all of these biological processes can occur. So the discharge velocity is not used to calculate that movement of water through the pore space. The seepage velocity is. So seepage velocity is that inside the soil, the rate at which it's moving inside it. So to do that, we would need our porosity. So you could take a sample of this, or like while they're compacting and creating this clay core, they could find the void ratio. And then if we know the void ratio, we can find the porosity. I just lost the tip from my head. That's weird. Anyways, I don't think I need it. So we could find the seepage velocity by, oof, I do need it. Let's see if this works. No, it does not. Yeah, it just came off. Can I borrow yours real quick? Thanks. No, it works. Cool. Okay. So for our seepage velocity, we know our discharge velocity is this. So this is our discharge velocity is equal to the porosity times the seepage velocity. And we already found our discharge velocity times 10 to the negative 4 centimeters per second. So if we just divide this, our seepage velocity is equal to 6 times 10 to the negative 4 centimeters per second divided by our porosity. Porosity is here. We always put that in percent form when we're calculating. And it should be equal to 1.9 times 10 to the negative 3 centimeters per second. So this is important. This value is important. Discharge velocity is important too, because we need to know like what the actual velocity is traveling into our stream or something. But when it comes to biological processes, when it comes to seepage for potential internal erosion, the discharge velocity or the seepage velocity is the thing that controls. Because look, the discharge velocity, wait, times 10 to the negative 3. Sorry, these shouldn't be negative. Maybe this is negative. This should be negative here. Right? Yeah, that's way too small. Yeah, that should be negative 4. Yeah, that's a typo. So negative 4, the discharge velocity is times 10 to the negative 4. But our seepage velocity is higher than our discharge velocity. So this is going to be the velocity that we would then design our soil samples against erosion, you know, because the discharge velocity could occur. And then if we have erosion, then it could propagate. And then we have that earth, you know, flood of water coming in like we showed in that first example. Okay, so that's it. If you're interested in learning more, I think I've shared this guy before. This guy's YouTube channel has a lot of cool like lab representations. And it's going to be really helpful because eventually we're going to start talking about flow nets. And he does these experiments where you can like visibly see the actual flow nets of laminar flow. So this is showing that it's laminar because these flow paths aren't crossing, right? If this was turbulent flow, then these things would be all over the place. All right, guys, see you in lab and see everybody else next Tuesday.